Alright, so today we're gonna solving the problem, the coin change 2. So we are given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. So we want to return the number of combinations that make up that amount. So if that amount of money cannot be made up by any combination of these coins, we will return 0. So in the description, they also said that we may assume that we have infinite number of each kind of coin. So that somehow hint us to think about like unbounded knapsack question pattern. So say we have the amount 5 and we have coin 1, 2, and 5. So there are basically 4 ways to make up this amount. If we just pick one coin that is 5, we basically reach our objective, so this valid. And if we pick 1 and then the coin 2, because we have infinite number of each kind of coin, so we can pick up the 2 twice, then 2 plus 1 will also equal 5. One thing to notice is that if we pick in a different order like 2, 1, and 2, it will be assumed as the same way of combinations. It's not a permutation question. And similarly, if we just pick one coin of 2 and then pick 3 coin of 1, and we will also get the 5. Or we can repeatedly pick the coin of 1 for 5 times, and then we will also have a valid result. So we will basically introduce 3 solutions. So the first one is basically the brute force way to determine whether we want to include or exclude the current coin. We call the number of coins as C and the amount as A. And then basically the time complexity will be big O of C to the power of A. It's basically a exponential time complexity, so it's not so efficient. Then we can use sort of memorization to reduce some repeated work, and then we will make reduce to C times A, and then basically we will use C times A space to record this memorization. And then we will finally introduce a most optimal solution, but it's kind of hard to come up with, which only use O of A time complexity. We will go through the brute force solution. We are starting from like the amount of 0, and we have like 3 choices, basically the 1, 2, and 5. And then we'll basically get the amount 1, 2, and 5. And then if we can reach the target amount, then we are done. This will be counted as one solution. Otherwise, we will continue to choose from the candidate's coin. So for this one, we will also have like 3 choices, 1, 2, and 5, which will result in 6, 3, and 2. And then the 6 is greater than the target amount, and this will not be counted. How to exclude duplicates? Say for this one, if we choose 2 here, and we'll get 3, and then choose another 2, we will get to the 5. So basically, the combination will be like 1, 2, and 2, right? But for choosing the coin of 2 at the first step, we can also like choose, like say the second step, we will choose like 1 that will result to 3, and another 2 to result to 5. Then we will basically have 2, 1, and 2. So they're basically the same combination, and we want to exclude the duplicates. So how are we going to do this? We will strictly limit that we can choose the coin that previously have chosen. Like for this 2, we cannot choose any coin from the 1. And for this 5, we can not choose either 1 or 2. We can just choose 5 or all other possible coins after the 5. We will erase this. And for this 2, we are gonna allowed to choose 2 and 5. So which will result 7 and 4. And 7 is greater than the target, we will not choose it. And then again, for the 4, we are still gonna choose like the 2 and the 5, and which will resulting the 6 and 9. Both of them are greater than the target amount, so both of them will not be valid. So this is kind of the brute force way, and the time complexity will be exponential, which will be c to the power of a. Because basically in every level, we will choose from all the coins, and for the a, it's the height of this tree. So if we choose all the way down to the bottom with 1, we will have 5 levels, so the height will basically be the 5. So it will be A. For implementation, how are we gonna implement that we will exclude the previous coins that we have chosen? So basically we will have sort of pointer, we will call it I. So in the first step, it will be point to the first coin. And then when we move to the next coin, we will strictly limit it not to like point to the previous coins. We can just use the 2 or the next 5. So we will gonna call it for as the DFS for now. So as we said, we will use the pointer to limit the choice of the coin. So we will input this I into DFS and also input a variable called total to record the current amount that we got. And then we will use another example to illustrate how we're going to use memorization to reduce some repeated work. So as we said before, we will use the DFS and input the I as the pointer to limit the choice of coin. And the total will be the current amount we have. So the target amount will be 4, and the coin, we will just have 1 and 2. I hope that can basically explain why we gonna have a memorization and how it works. So to get started, we're starting from the amount of 0, and we basically wanna include 1 or not include 1. So here we got a index 0 to include 1, and there we just wanna to exclude 1 and just to use 2. So the I will be 1. We will leave this branch for now and to go all the way to the bottom of the left branch and to see what we will get for the memorization dictionary. So first we choose the coin of 1 and we will get the total sum of 1. And then go to the left branch, we will keep using the coin of 1 and we will get 2. And then keep using 1, get 2, get 3, and keep using 1 to get 4. And this is the target amount we're gonna reach. So at this point, the I is 0, and the total, here we will just simplify it to T for easy notation. The T is the 3. And then we'll basically have one way to do that. And then for the right branch, it results to the 5, which is greater than the target, so it's not possible. We will also record this into the memorization. So we have one way here, so this will return to here, and then basically I0, T2 will also be 1. And for the right branch, the I equals 1, and the total will be 4, so which is also the target amount we want to have. So the I equals 1 and the T is also the 2. So we will also hand it into the memorization. And then, and interesting is that we can stop for the left branch for now and to go for the right branch. So we choose the 2 for the first pick, and we will result in the sum of 2. And then, because our index is currently the 1, so we cannot go back to the index of 0, which is the coin of 1. We can only choose the coin of 2. So here, I want to mention is that the index will keep being 1, and the current total is 2. So what we will get? So we can look up into our memorization and to see that I equals 1 and 2 equals 2 is in the memorization, which result in one way to get the target sum. So we can directly use this memorization and do not explore all the possible exploration for its children. So we can basically return 1 to the root node. So this is how we use memorization to reduce our repeated work. And for the time complexity, because the choice of I is limited by our number of coins, and the T is basically up to the amount. We will basically have like big O of C times A time complexity. And then we can complete our work to finish the left branch. So for here, we choose the 2 and the index is 1. So for future steps, we can only choose 2. So that will result to 5, which is greater than the target. So that will also be infinite, or 0 ways to construct a target. And then for here, we got a 1 from the left and the 1 from the right. So we will basically have 2 ways to do that. And we will all the way return back to here, and plus the right and left, we will got 3 ways. If we look into the combination, we will see that it's 1 1 1 1 for the first one, and the like 1 1 2 for the second one, and 2 2 for the last one. And then we will try to solve this using dynamic programming, which will be more efficient if we can evolve to the optimal solution. So first we will have a 2D grid. The row will be the amount and the column will be the coin that we have. So the amount is like the 5, and we're starting from the 0 and 1, 2, 3, and 4. So each cell in the grid will determine how many ways can we use these coins to sum up to the amount. So how many ways can we use like coin 5 to sum 0 or 2 or 1? So it's just one way, right? Just no coins. And then for this row, it means that we can only use the coin of 5. And for this row, we can basically use these 2 coins, and for this row we can basically use all these 3 coins. So we were starting from the bottom, so it's a bottom-up dynamic programming. So first we will use coin 5 to see if we can sum up to 1. It's not possible, so it will be 0. And for 2, also 0. And for 1, it equals the amount of 1, and we will minus the 1, we will result in the 0. So we have one way to sum up to 0, so we will have a 1 here. And then continue. So for the 5, how many coins can we use to sum up to 2? Still the 0. And for the 2, it's basically the same as the previous one, so it's one way. But for this row, how many ways can we use all these numbers to sum up to 2? So for this, only 1, 2 minus 1 is 1. We have one way to sum up to 1. Then we will have like one way to use only the coin of 1 to sum up to 2. But also we need to look up the cell that next row, which is how many ways can we use the coin 2 to sum up to 2. It also have like one way. So we need to add up them. So 1 plus 1 will be equals 2. Then I will be faster to do this. So for the 5, still the 0. And for this cell, the 3 minus 2 is 1. So how many ways can we sum up to amount 1 using coin 2 or 5? It's 0. So it's 0 here. And then for the 3, there were 2 ways to sum up to 2 using 1, 2, and 5, and 0 ways to just use 2 and 5. So also 2 here. For the 4, 0 here. For the 4, we will minus 2 to have 2 one way. So one way here. And then for the 4, so 4 minus 1 is 3. We have 2 ways to sum up to 3 and one way to just using 2 and 5, so sum them up will equal to 3. And then for the 5, we have one way to use coin 5 to sum up to 5, and 5 minus 2 will be 3. We have 0 ways to sum up to 3 just using 2 and 5, so we have 0 way from the left, but one way from the bottom, so 1 here. And for this, similarly, we can just add up 3 and 1 will equal to 4, and we basically get the answer. So basically, for every arbitrary cell, we need to look up the right to see if there is any possible answers that we can reuse, and also to look one cell down to see the next row if we have like something that we can reuse. So similarly for this arbitrary position, we also need to like look to the right and look to the down. So basically we need to maintain this 2D array until we finish our iteration. However, if we can try to solve this in another direction. So previously we solved it like to row by the column by column, right? How about we solve it row by row? So similarly for the 5, we have 0 ways to sum up to 1, 0 ways to 2, 0 ways for 3, 0 ways for 4, and 1 way for the 5. And for the 2, 0 ways for this 1 way for the 2, 0 way for the 3, and like 1 way for the 4. And at this position, what are we gonna do? So first we will look to the right to see the 3, which is 0, and then look one position down, which is 1. So we gonna add to 1 here. And then basically for any arbitrary position on this row, we will never say reuse the number in this row, right? So we can basically remove all these rows. What we're going to use is just exactly one row down to the target row. So that can basically reduce the space like 1D dp. First, we will try like the coin 1. So we have one way to sum up to 1, and then one way to sum up to 2, one way to sum up to 3, one way to sum up to 4, one way to sum up to 5. And then for the coin of 2, we have like 0 way to sum up to 1, so we'll keep 1 here. But we do have another way to sum up to 2, so we will add 1 here. And then 3 minus 2 is 1, and we have one way to sum up to 1, so we will plus 1 here. And for the 4, we already have like 2 ways to sum up to 2, so we will add 2 here. And for the 5, we have 2 ways sum up to 3, so we will add 2 here. And then for the 5, we basically have 0 ways to sum them up. But for the 5, we do have one way to sum up to 5. So we will plus 1 here. So that will also get the 4, but we reduce the space complexity to 1D array. And then let's see the code. As this video gonna be like too long, so I would just not code it from scratch. I would just copy and paste here and explain how it works. So for the brute force way, like we said before, we will use a cache to reduce some repeated work. So for the DFS, we will basically input the index to limit the choice of coin and the total to determine whether we reach the target amount. So let's see some base case. So if we reach the target amount, so the total equals to amount, we will just return 1 as we have like one way to reach the target. Otherwise, either the current amount is greater than the target or the current index is out of bound, like we just have like 2 candidate coins, but the index maybe go to the 3 or 4, we will just stop here and return 0 ways. Also, that's basically how we use cache here. If the current index and the total and the current amount is in the cache, we will just reuse that. So that's how we use like say I equals 1 and total equals 2 in the previous illustration that we first have a like 1 and 1 in the left branch, and we chose the next 2 to make it to 4. And for another, the right branch, we first choose the 2. So basically the first total number, the 2 from 1, 1 and the 2 from 2 are the same. And we know that this has been in the memorization. We can directly use this when we want to explore the children of the 2. So we can basically just return the cache, which is one way. And then for this line, that's basically to include the current index and add the current coin to the total current amount, or we will exclude the current index coin and move to the next to exclude the previous coins. It's like the left and right branch. And then the return value will be add up and be recorded in the cache. And then for the 2D DP solution, we will basically have a O of C times A, time complexity and space complexity. So I'm gonna explain how it works. So we will first have a initialize a DP and switch the amount and the coin in the implementation, so that we can simply initialize once for the first row as amount. So basically, we will iterate through each amount with all the coins with a nested loop. So as we illustrate in the previous part, we will, starting from this cell, which is the first row in amount and the last column and the coins. So basically, we will first to check the left part. Say like for this row, it means that we only use the coin of 5, and for this row, we are allowed to use both 2 and 5. And for this column, we are allowed to use all these 3 coins. So we should first add the ways that we calculated before using other coins. So first we have like 0 for the 5 here, and then 0 here and 1 here. And then basically, to make our process faster, I will fill in some number here. Okay, so for this position, we will first initialize it with the right column, so it's 1, and then we will see the amount, the current amount, which is 2, to minus the coin, which is 1, so that will result in 1, and we have one way to construct the amount of 1 previously, so we will add it onto this cell, so that will be 2. So basically that's the process, and in the end we will basically return the last row, the first column of the last row, which will be the end of our process. And then lastly, I will show the 1D dynamic programming, which is the optimal solution that only use the O of A space complexity. So first we will construct this 1D array SDP. So I write some comment here for visualization. So for the 0 index, we have one way to construct the amount of 0, and then we'll basically traverse through all the coins. For each coin, we were starting from index of the coin, so that we don't need to like reprocess some impossible solutions. Say like if we have like 5 here, we will just to see whether we can construct the amount of 5 instead of to see some amount smaller than the current coin. And then basically for the 1, we all have like one way to construct each amount to add them up. And for the 2, so we were starting from amount 2. And then we have one way to construct 2 previously, and 2 minus 2 will be 0, and we have one way to construct 0, so we will add 1 onto the number of 2, so that will be 2. And then for the 3, so 3 minus 2 will be 1, and we have one way to reach the amount of 1 previously, so we will also add it onto the current numbers. That will also be 2. And for the 4, 4 minus 2 is 2, and we previously have 2 ways to construct 2, so we will add 2 here. And similarly for the 5, 5 minus 2 is 3, and we have 2 on a 3, so we will also add 2 on to the current ones. That will also be 3. And then for the 5, we were just starting from this 5, and we have 5 minus 5 is 0, and we have one way to construct 0, and then we will just add 1 onto this current 3. That will be 4, and that will be the final result. Then when we run it, it's basically efficient on time and memory. I hope this video and all these solutions make sense to you, and hopefully dynamic programming is somehow a difficult problem, and I hope you can using this question to somehow practice this kind of questions.